Chapter 10, Part 1, Radiation Dose in CT. We are going to begin by discussing some quantities and units of radiation dose applicable to CT. The main ones we will be discussing are exposure, absorbed dose, and effective dose. To start out with exposure, this is the radiation quantity, so the quantity of radiation at a particular point on the patient. An easy way to measure is with an ionization chamber positioned at the point of the measurement. Radiation falling on the ionization chamber ionizes the air in the chamber to produce ion pairs, or charges. Exposure is a measure of the amount of ionization produced in a specific mass of air by X-rays or gamma radiation. The ionization indicates the amount of radiation to which a patient is exposed. The conventional unit for exposure is the Rankine, and the SI unit is the Coulomb per kilograms. And exposure is reported usually in millirankines. Moving on to absorbed dose, this is radiation dose, the amount of energy absorbed per unit mass of material. And any risk associated with radiation is related to the amount of energy absorbed. And this quantity is particularly important in radiation protection. The old unit of absorbed dose is the rad, and the SI unit is the gray. 1 gray is equal to approximately 1 joule per kilogram. Usually when we refer to grays, we refer to milligrays, where 1 milligray equals 100 millirads. This G is supposed to be an R, so millirads. Or it can be said as 1 rad is approximate to 0.01 gray. Next, we will discuss effective dose. This is used to quantify risk from partial body exposure to that from an equivalent whole body dose. It takes into account the type of radiation and the radiosensitivity of different tissues, as we all know that some tissues are more sensitive than other tissues. It is known as E, a capital E, and it is the weighted average of organ doses. The old unit of effective dose is the rem, and the SI unit is the sievert. And 1 sievert is equal to 100 rem. The effective dose relates exposure to risk, such as cancer and induction of genetic effects on patients. Effective doses from fluoro and CT exams are comparable to natural background radiation, which is about 3 millisieverts per year. The occupationally exposed individuals, so the radiologists and the technologists, are given in millisieverts. The dose limit for radiation workers is 50 millisieverts per year in the United States. Okay, so one of the reasons why I broke Chapter 10 down into 2 lectures is just because there's a lot of information in this chapter. And as you can tell, there's a lot of information on this slide as well, but it's all important. One of the reasons that techs and rads should really understand the dose in CT is due to radiation bioeffects. These effects are categorized into either stochastic or deterministic effects, So first, we will discuss stochastic effects. These are effects for which the probability, rather than the severity of the effect occurring, depends on the dose. So the probability increases with increasing dose, and there is no threshold dose for these effects. The linear no threshold, also known as the LNT, dose response model, is the radiation risk model that is most favored by radiobiologists in estimating the risk of exposure in radiology. Medical radiation protection standards, guidelines, and recommendations are based on the LNT model. The LNT dose response model states that the radiation risk increases as the dose increases, and there is no threshold dose. The model is more commonly used since it has a simple and conservative approach, which is more likely to overestimate cancer risk at low doses than to underestimate the risk of cancer. But because of medical imaging, the radiation doses are so low, there is no evidence that the no threshold model is effective at estimating cancer. However, even a small dose does have the potential to cause a biological effect. There is no risk-free dose with the stochastic effect. If harm does occur, the damage generally becomes apparent years after the exposure, which is why the stochastic effects are also called late effects. Examples of stochastic effects are leukemia, other cancers, and hereditary effects. They are considered a risk form exposure to the low levels of radiation used in medical imaging, including NCT. With deterministic effects, these are known as non-stochastic effects. It deals with the severity of the effect rather than the probability of the effect, and it increases with increasing dose for which there is a threshold dose. Below the threshold dose, these effects are not observed. Threshold doses are considered to be relatively high doses that can kill cells and cause degenerative changes in tissues that have been exposed to radiation. These are also referred to as early effects and involve high exposures that are unlikely to occur in medical imaging. Some examples of deterministic effects include skin redness, epilation, and pericarditis. As patients undergo several exams, it may be possible to reach the threshold dose for certain deterministic effects. It's obvious that the geometry of the X-ray beam and the way the patient is exposed to the beam is different in regular radiographic imaging and in CT imaging. So in CT, the exposure pattern is different than in conventional radiography because of the geometric aspects of the beam and just the scanning procedure itself. Usually the beam is well collimated to describe a fan-shaped beam that rotates around the patient at least for 360 degrees in CT. And the tube is not fixed like in radiography, but it is in several positions during one complete revolution around the patient. In multi-slice scanners, the fan-shaped beam has now become a cone-shaped beam, and the dose distribution pattern is more uniform in CT than in regular radiography because the X-ray beam is rotating 360 degrees around the patient's body. As we know, beam geometry refers to the size and shape of the X-ray beam from the tube and passing through the patient to strike a set of detectors that collects radiation attenuation data. The longitudinal axis of the patient is the z-axis, and intensity of radiation beam along the axis would have equal intensity everywhere inside the beam and would have no intensity on either side, ideally. On a graph, it has a flat top and steep sides, as is the same width as the X-ray beam. Take a look at figure 10.4 in your book to understand what I mean. However, in reality, the radiation intensity measured along the z-axis actually has smoother edges and appears as a bell-shaped curve on the graph. Dose distribution describes the arbitrarily shaped dose intensity along the patient axis. This shape varies among CT scanners and is extremely important to dose in CT because it is the dose distribution measured. The instrumentation and methods used to measure the patient dose from a CT scanner is referred to as CT dosimetry and is very different than the dosimetry of conventional radiography. CT dosimetry is an important concept for techs to understand regarding radiation dose in general. Dosimetry involves the measurement of the dose to the patient, and it is characterized by several metrics that refer to radiation dose quantities and their associated units. We'll take a look at a few different types of dosimeters used to measure CT doses, CT dosimetry phantoms, and dose descriptors specific to CT. There were several different types of dosimeters that were used in the past to measure dose in CT. These include film dosimeters, thermoluminescent dosimeters, which are also known as TLDs, and specially designed ionization chambers. So in this picture right here, A is the ionization chamber right here. B is just the phantom itself, the whole big thing right here. And C is the digitizer, and D is actually the dosimeter. The ionization chamber is an instrument used to accurately quantify radiation exposure. It consists of a small air-filled container with thin walls that allows radiation to pass through easily. As the high-energy photons, or the X-rays, collide with air molecules enclosed within the ionization chamber, some of the molecules are ionized. These free electrons can be collected on a conducting wire or plate and measure as electric charge. The amount of collected charge is proportional to the amount of ionization, which is proportional to the amount of radiation that passes through the chamber. The charge is removed from the ionization chamber and measured with a very sensitive instrument known as the electrometer. the total electric charge generated by the X-ray beam is represented by Q and measured in coulombs. The ionization chamber is centered in one of two cylindrical phantoms during radiation measurement. The smaller phantom simulates a patient's head, and the larger one simulates the patient's body or the torso. Both are 15 centimeters long, and the diameter of the head is 16 centimeters, while the diameter of the body is 32 centimeters. Both are solid acrylic with holes drilled through the phantom at specific locations to accommodate the pencil ionization chamber. Acrylic plugs are placed in the holes unoccupied by the chamber, and the appearance of the hole in the image verifies that the X-ray beam is striking the center of the phantom. The procedure for measurement is to place the ionization chamber in one of the phantom holes, take a scan, and then record the amount of charge emitted from the chamber. Then the chamber is moved to the next hole. The plug is placed in the original chamber hole, and the procedure is completed. Moving the chamber to another hole allows the dose to be determined at a variety of locations within the phantom. Generally, the dose varies among locations, even when the same dose technique is used, so it's necessary to measure the dose at several locations for a given technique. There are 3 dose metrics commonly used in CT, and 2 of which are shown on the dose report that displays on the CT scanner console that you may see at your site. These include the CT dose index, which is known as the CTDI, and the dose length product, also known as the DLP. The third is effective dose. This relates to radiation exposure to risk, and CTDI and DLP are both expressed in milligrays, and the effective dose is expressed in millisieverts. Effective dose is considered the best method available to estimate the stochastic radiation risk. However, just remember it is only an estimate. Multiple scan average dose, also known as MSAD, is the first CT dose descriptor to be identified and used. To use, a series of CT scans is performed on the patient, and the patient is moved a bed index distance between each scan, and each slice delivers the characteristic bell-shaped dose. So if doses from all scans are added up, then the resulting total patient dose resembles the oscillating curve. Take a look at figure 1010 and 10.9 in your book to see the curves. Where the bell curves overlap, this means that the resultant dose is higher than that from just one scan. If total dose distribution curve is known, then the MSAD can be calculated by mathematically sampling the peaks and valleys of the multiple scan dose curve. So take a look at the equation right here. You can see that to calculate the MSAD, you take the CTDI times the slice width over the bed index. In the formula, the slice width is in millimeters, and the bed index is also known as slice spacing. CTDI was the next dose descriptor after the MSAD to be used. It was developed by the FDA, and it actually represents the mean absorbed dose in a scanned object volume. And it's actually evolved through many changes over time. Initially, it could only measure 14 contiguous slices, and then the CTDI 100 was introduced, and this was developed to cover the calculation of an index for 100 millimeters along the length of the entire pencil ionization chamber. And this is regardless of the slice width being used. The next change in the CT dose descriptor is the introduction of the weighted CTDI. It accounts for the average dose in the XY axis of the patient instead of the Z axis. And this is accomplished using a phantom where the pencil ionization chamber is positioned in the center and at the periphery of the phantom. The CTDI volume was developed to consider dose in the Z-axis, and it is calculated by taking the weighted CTDI divided by the pitch. And remember, pitch is the distance the table travels per revolution in millimeters to the total nominal beam collimation in millimeters. The dose length product provides a measurement of the total amount of exposure for a series of scans, and it can be calculated if the length of the irradiated volume and the volume CTDI are known using this formula right here on this page. The DLP is directly proportional to the scan length, so you know that if the scan length increases, then the dose length product will also increase. The effective dose relates to the exposure to risk. So it takes into account the different tissues that have different radiosensitivities and absorb dose to specific organs. Example, the gonads are more sensitive than the brain tissues. And the risk of stochastic radiation response is proportional to the effective dose rather than the tissue dose, since only the parts of the body, not the entire body, are exposed in medical imaging. Effective dose can be calculated by this formula, and it is given in sieverts for the SI unit, but the old unit is the rems. And it's important to know that 1 sievert is approximately 100 rem. To keep this simple, we need to know that the effective dose is calculated by multiplying the DLP by the constants referred to as the K values right here. And these K values have already been established according to body parts. Then we know that we can use the formula, the constants times the dose length product equals the effective dose. The effective dose allows for a comparison of the dose received from the CT scanning with the dose received from the natural background radiation. And I don't necessarily need you to know the top formula as much as the effective dose formula down here.